Alrighty, now that we've learned what convolutional layers are, I've created a simplified diagram here that we'll work with. And I've added convolutional layer to our arsenal of layers. Now that we have these, we're going to build a classic architecture. So we're going to build LeNet-5, which is the network from the 1990s that was able to read digits on zip codes. And we've talked about it before. We talked about it in our introductory slideshow, and we're gonna now be building it. So this neural network has a couple of convolutional layers that feed into a dense layer, and it builds on the deep net that we've already built in Keras. So if you want to follow along with a completed notebook, you can click on this LeNet in Keras notebook here, which is already done, or like me, you can copy the DeepNet in Keras demo notebook that we've already been building, and we can continue to build it into this deep convolutional LeNet-5. So that's what we're going to name this. LeNet in Keras. For me, it's a demo. And we can change the name here. So we could call it a deep convolutional neural network, or you just say LeNet-5, whatever you want to title this. And this is going to be a deep convolutional neural network to classify the MNIST digits. Let's clear the outputs that we had from the DeepNet. We're going to set a seed for reproducibility, just like before. We have some different dependencies, so of course we're still loading in the MNIST data, we're still building a sequential model, we're going to have dense layers, we're going to have dropout layers, we're also going to have a few new layers now. So we're going to have all of these new guys. We're going to have a flatten layer, which we've talked about earlier. We're going to have a max pooling layer, which we talked about earlier. And we're going to have a convolutional layer as well. Because these MNIST digits just have darkness, they don't have any color. We don't need anything three-dimensional. We're just working with 2 dimensions here. So there we have our dependencies. We're going to load our data the same as before. We're going to pre-process our data the same as before. And now we're going to design a different neural network architecture. So we can clear out all of these layers that we had before from our DeepNet, and we are going to build from scratch. So first off, we're going to have a convolutional layer right at the start taking in the inputs. So this is going to be a 2-dimensional convolutional layer, and we have to decide how many neurons we're going to have. Well, the LeNet-5 had 32 neurons in its first convolutional layer, so we're going to go with that as well. Let's type in 32, and we need to decide on a kernel size. So the kernel size, or the pool size, is the size of the filter that will be passed along the image, and we're going to have 3 by 3 pixels is our kernel size. So we specify that like this. And as with the dense layers, we've become very familiar with ReLU activation, so we're going to stick with that. And we have to specify the shape of our input. So that is the size of the input image. As always with these MNIST digits, we have 28 pixels by 28 pixels. The MNIST digits are black and white, so there's only one depth dimension to worry about. With color images, we'll have 3. We can worry about that later. And that first convolutional layer is going to feed into a second convolutional layer. This one's going to have 64 neurons, or filters, or kernels. They're all synonyms. So We're going to have 64 in the second layer. Our kernel size is going to stay the same. It's going to be 3 by 3. Our activation is going to be the same. It's going to be ReLU. And then to make the computational complexity a little bit smaller, well, a quarter of the size, at this layer we're going to have max pooling, where for every 4 pixels we're going to reduce them to 1. So by selecting a 2 by 2 pool size, we're just selecting the strongest activation from amongst every 2 by 2 pixel square coming out of the convolutional layers. And then we're going to add some dropout so that our results from training apply well to the validation data. And we're going to drop out a quarter of the neurons here. Somewhat arbitrary choice that I've figured out works well. We're going to flatten everything here. So we have more than one dimension at this point, but the dense layer that we're going to pass into, the fully connected layer, that's going to be able to recombine all of these possible representations stored by these convolutional neurons. So we have so each convolutional neuron is representing some space invariant kind of 3 by 3 representation, some kind of edge or some kind of corner. And now we're going to feed all of that into a dense layer that allows us to recombine all of these various shapes represented by the convolutional kernels into any kind of configuration. So in order to get from this multi-dimensional space into a one-dimensional array that the fully connected layer can handle, we need to flatten. And then we can add the dense layer here. And the dense layer, this is the same as we were doing before. We're going to have 128 neurons, and we're going to have ReLU activation. We're going to drop out half of those neurons in the fully connected layer with each training step. I've chosen different proportions of dropout, a quarter and a half for the convolutional and dense layers respectively, and that's just because I happen to find it to work well. We'll talk a bit later on about how to select these individual hyperparameters. And then finally, we need to output some probability. So we have an output layer with our number of classes, which is 10, representing each of the 10 digits, as always. And we choose softmax activation so that the outputs represent some probability as to the strength of the guess for a particular digit. So let's see if this model works. Yes, it does. Let's look at the model summary. So now we have way more parameters than before. We've gone over 1 million, and a lot of those are contributed by the dense layer. So the convolutional layers are actually relatively efficient, and that's because they have this property where they're just actually representing this small space, but they're representing that small space anywhere on the image. So very, very efficient. It's the dense layer that's adding all these weights. So once we have the representations, the space invariant representations inferred by the convolutional layer, the fully connected layer is recombining those. So let's see how this works. We are going to stick with the kind of compilation parameters that we had before. So we're going to continue to use cross-entropy cost. We're going to continue to use atom optimization in our gradient descent, and our metric to monitor how our network is performing is going to continue to be accuracy. And now we can train. It's going to take longer to train each epoch than before. Let's try it out on just one first. All right, so I have an error here, and it says that it expected a 4-dimensional input, and we got a 1-dimensional input. Now, that's because we worked precisely from our DeepNet notebook, which was only using dense hidden layers, didn't have any convolutional layers. And so when we pre-processed our inputs, we had a 1-dimensional array that we were creating from our 2-dimensional MNIST digits. But in fact, now that we're feeding into a convolutional network, we want to take advantage of that 2-dimensional image. And so we're switching our inputs from 784 by 1 to 28 by 28. And so we can specify that here. We still are saying that the 4th dimension is 1 because we don't have color. These are monochromatic images. So let's restart and run all and see if that fixes the error. I'm reasonably confident about it. Yep, there we go. So our model is fitting. Now you can see before our models were fitting in 2 seconds, 3 seconds, 4 seconds. I think the longest we've seen for the first epoch was 7 seconds. Now this one is going to need to train for about a minute. And the reason for that is that we have so many more trainable parameters than we did before. So this will take a while, but luckily I already know the results. So we can talk about those while we wait. Now, we're going to see something pretty amazing. The validation accuracy after just a single epoch should be 98.4%. Now recall that previously our best validation accuracy was 97%. So these convolutional layers that are specialized for these kinds of machine vision tasks really did the trick. Now, after a handful of epochs, it continues to get better. Our validation accuracy will be above 99%. And after training for 20th epochs, I was seeing up to 99.3% accuracy. So there we go. As I said we would have, our validation accuracy after just a single epoch is 98.4%. So that blows our previous results out of the water. So I encourage you at home to run this for more epochs. You can run it for as long as you like. And one thing that you want to keep an eye on is that you're not using too many resources on your machine. So a handy little way to look at that is in your terminal. You can, from anywhere, use the htop command. You might have to install that on your machine, which is easy with apt-get install htop if you don't already have it. And then htop shows you how many resources you're using on each of the cores on your machine. And you can see that we're using quite a bit of each of the 16 CPUs available on this machine. But we're not using very much of the memory, which is the thing that we should really be worried about. If our data set was too large and we were using batch sizes that were too big, we could run out of memory, and our learning would be intractable with our neural network. So that's one thing that you want to look out for. Now, back to our model here. It's continuing to learn. And there's all kinds of parameters here, hyperparameters that could be configured. We've got the number of neurons in the convolutional layers, the kernel size. We've got the pool size in our max pooling layer, a dropout, number of neurons in this dense layer. We could have maybe more dense layers. There's all kinds of hyperparameters that we could change here. We're going to talk about that later on in these live lessons. For now, we're going to get into some more exciting data. So up to this point, we've been working with MNIST digits And I think now that we've been leveraging convolutional layers, we have more or less cracked this problem. With this current configuration, we'll be 99.3% accurate by the 20th epoch, and that means that out of 10,000 images, we're only misclassifying 70. Really remarkable. And some of those 70, if you have a look at them, they are really difficult digits for even a human to distinguish. So I feel like it's time for us to move on from these MNIST digits, and we're going to have a crack at the Oxford Flowers dataset.